According to the National Electrical Code, for a 400 amp service to a large building, a minimum of 3 number 4 American wire gauge conductors is required for the main feeder. The feeder must be sized in accordance with the ampacity requirements of the largest feeder it supplies. The building grid is not considered a grounding electrode in this scenario. Therefore, it is not permissible to run a single number 4 conductor around the building to supply all the feeders. You must use a minimum of 3 number 4 conductors for the main feeder and size the other feeders accordingly. Now let's delve deeper into the specifics of conductor sizing, ampacity, and the relevant code requirements. When dealing with a 400 amp service, the selection of appropriately sized conductors is paramount for ensuring the safe and efficient operation of the electrical system. The National Electrical Code, or NEC, provides comprehensive guidelines for determining the minimum conductor size based on the service amperage and the anticipated load. The general rule is that the conductors must be sized to handle the continuous load plus 125% of the non-continuous load. In the case of a 400 amp service, the conductors must be capable of carrying at least 400 amps continuously. However, this is just the starting point. The NEC also mandates that the conductors be sized based on the ampacity requirements of the largest feeder they supply. This means that if the 400 amp service is feeding multiple subpanels or other buildings, the conductors must be sized to accommodate the combined load of all downstream devices. Furthermore, the NEC specifies different ampacity ratings for different types of conductors based on their insulation material and installation method. For example, conductors installed in conduit typically have a lower ampacity rating than conductors installed in free air. Therefore, it is crucial to consult the appropriate NEC tables to determine the correct ampacity rating for the selected conductors. In addition to conductor sizing, the NEC also addresses the issue of voltage drop. Voltage drop occurs when the voltage at the end of a conductor is lower than the voltage at the source due to the resistance of the conductor. Excessive voltage drop can lead to a variety of problems, including reduced equipment performance, overheating, and even fire hazards. To minimize voltage drop, the NEC recommends limiting the voltage drop in feeder circuits to 3% and the voltage drop in branch circuits to 5%. The length of the feeder should be kept as short as possible to minimize voltage drop. This can be achieved by locating the service panel as close as possible to the load center. Another important consideration is overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overheating and damage due to excessive current flow. The NEC requires that all conductors be protected by overcurrent devices sized to match the ampacity of the conductors. Proper overcurrent protection must be provided for all feeders and subpanels. This means that if the conductors are rated for 400 amps, the overcurrent device must also be rated for 400 amps or less. It is important to note that the NEC prohibits the use of overcurrent devices that are larger than the ampacity of the conductors they protect. Finally, the NEC addresses the issue of grounding and bonding. Grounding is the process of connecting electrical equipment to the earth to provide a path for fault current to flow back to the source. Bonding is the process of connecting different metal parts of an electrical system together to create a low-impedance path for fault current. The building grid should be installed in accordance with the NEC requirements for proper grounding and bonding. The NEC requires that all electrical systems be properly grounded and bonded to ensure the safety of people and equipment. In the specific scenario of a large pole building with a 400 amp service feeding a 200 amp subpole and other smaller buildings, several key aspects must be carefully considered to ensure compliance with the NEC and maintain a safe and reliable electrical system. Firstly, the main service conductors from the utility transformer to the main disconnect in a pole building must be sized to handle the entire 400 amp service. As previously mentioned, a minimum of 3 number 4 American wire gauge conductors are required. However, depending on the specific load calculations and conductor types used, larger conductors may be necessary to meet the ampacity requirements and minimize voltage drop. It's essential to perform a thorough load calculation that accounts for all connected loads, including lighting, receptacles, equipment, and any future expansion plans. This calculation will determine the total demand load and ensure that the service conductors are adequately sized. Secondly, the feeder conductors from the main disconnect to the 200 amp subpanel must be sized to carry at least 200 amps. Again, the specific conductor size will depend on the conductor type, insulation, and installation method. It's also crucial to consider the distance between the main disconnect and the subpanel, as longer distances will result in greater voltage drop. To mitigate voltage drop, it may be necessary to upsize the feeder conductors. Thirdly, the conductors feeding the other small outbuildings must be sized according to their individual load requirements. Each outbuilding should have its own dedicated circuit with appropriately sized conductors and overcurrent protection. It's important to avoid overloading any single circuit, as this can lead to overheating and potential fire hazards. Fourthly, the grounding and bonding system must be properly installed to ensure a safe and effective path for fault current. This includes grounding the main service entrance, bonding all metal enclosures and equipment, and installing a grounding electrode system. The grounding electrode system typically consists of one or more ground rods, ground plates, or metal underground water pipes that are connected to the grounding busbar in the main service panel. Fifthly, overcurrent protection must be provided for all circuits and equipment. This includes circuit breakers or fuses in the main service panel, the subpanel, and any other distribution panels. The overcurrent protection devices must be sized to protect the conductors from overloads and short circuits. It's essential to use the correct type and size of overcurrent protection device for each circuit. Sixthly, the built-in grid should not be used as a substitute for a proper grounding electrode system. While a built-in grid can provide some level of grounding, it is not designed to handle the full fault current that may occur during an electrical fault. Therefore, a dedicated grounding electrode system is always required. Seventhly, all electrical work must be performed by a qualified electrician who is familiar with the NEC and local electrical codes. Electrical work can be dangerous, and it's important to hire a professional who has the knowledge and experience to do the job safely and correctly. In summary, installing a new 400 amp service for a large pole building requires careful planning and attention to detail. It's essential to follow the NEC and local electrical codes to ensure a safe and reliable electrical system. By properly sizing the conductors, providing adequate overcurrent protection, and installing a robust grounding and bonding system, you can minimize the risk of electrical hazards and ensure the long-term performance of your electrical system. Remember, the information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before undertaking any electrical work. The National Electrical Code, or NEC, is a comprehensive set of standards that govern the safe installation and maintenance of electrical systems. It is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. The NEC covers a wide range of topics, including conductor sizing, overcurrent protection, grounding, bonding, wiring methods, and equipment installation. It is essential for electricians, electrical engineers, and building inspectors to be familiar with the NEC to ensure that electrical systems are installed and maintained in accordance with industry best practices. The NEC is not a law, but it is widely adopted by state and local governments as the basis for their electrical codes. This means that compliance with the NEC is often legally required. The NEC is published by the National Fire Protection Association, or NFPA, a non-profit organization that develops and publishes codes and standards for a wide range of industries. The NFPA is committed to reducing the risk of fire and other hazards through the development and dissemination of safety information. The NEC is available for purchase from the NFPA website and other online retailers. It is also available for free viewing at many public libraries. In addition to the NEC, there are other electrical codes and standards that may be relevant to a particular project. These include state and local electrical codes, as well as industry-specific standards. It is important to be aware of all applicable codes and standards before beginning any electrical work. Electrical work can be dangerous, and it is essential to take all necessary precautions to protect yourself from electrical shock and other hazards. Always turn off the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not comfortable working with electricity, hire a qualified electrician to do the job for you. Electricity is a powerful force, and it should be treated with respect. By following the NEC and other applicable codes and standards, you can ensure that your electrical system is safe and reliable. Always consult with a qualified electrician before undertaking any electrical work. Remember, safety is always the top priority. Now let's delve into some specific examples of how the NEC applies to conductor sizing and overcurrent protection in a 400 amp service. Suppose you are installing a 400 amp service to a commercial building that will house a restaurant. The restaurant will have a variety of electrical loads, including lighting, cooking equipment, refrigeration units, and HVAC systems. To determine the appropriate conductor size for the main service conductors, you must first perform a load calculation. This calculation will take into account all of the connected loads and determine the total demand load. Once you have determined the demand load, you can consult the NEC tables to find the appropriate conductor size. For example, if the demand load is 350 amps, you would need to use conductors with an ampacity of at least 350 amps. According to NEC Table 310.16, 3 number 3 American wire gauge copper conductors with type THHN insulation installed in conduit would be sufficient to carry 350 amps at an ambient temperature of 30 degrees Celsius. However, if the ambient temperature is higher, you may need to use larger conductors to compensate for the dirting factors specified in the NEC. In addition to conductor sizing, you must also provide adequate overcurrent protection for the main service conductors. The overcurrent protection device, such as the circuit breaker or fuse, must be sized to match the ampacity of the conductors. In this example, you would need to use a 350 amp circuit breaker or fuse to protect the number 3 American wire gauge conductors. It is important to note that the NEC prohibits the use of overcurrent devices that are larger than the ampacity of the conductors they protect. Now let's consider another example. Suppose you are installing a 400 amp service to a residential building that will have a swimming pool. The swimming pool will have a variety of electrical loads, including a pump motor, a heater, and lighting. To determine the appropriate conductor size for the feeder conductors to the swimming pool equipment, you must first perform a load calculation. This calculation will take into account all of the connected loads and determine the total demand load. Once you have determined the demand load, you can consult the NEC tables to find the appropriate conductor size. For example, if the demand load is 60 amps, you would need to use conductors with an ampacity of at least 60 amps. According to NEC Table 310.16, 3 number 6 American wire gauge copper conductors with type THHN insulation installed in conduit would be sufficient to carry 60 amps at an ambient temperature of 30 degrees Celsius. In addition to conductor sizing, you must also provide adequate overcurrent protection for the feeder conductors to the swimming pool equipment. The overcurrent protection device, such as a circuit breaker or fuse, must be sized to match the ampacity of the conductors. In this example, you would need to use a 60 amp circuit breaker or fuse to protect the number 6 American wire gauge conductors. It is important to note that the NEC has specific requirements for the installation of electrical equipment near swimming pools. These requirements are designed to protect people from electrical shock hazards. Always consult with a qualified electrician before installing any electrical equipment near a swimming pool. Finally, let's consider an example of voltage drop calculations. Suppose you are running a 240 volt circuit to a piece of equipment that is located 200 feet from the service panel. The equipment draws 20 amps. You are using number 12 American wire gauge copper conductors with type THHN insulation. To determine the voltage drop in this circuit, you can use the following formula: voltage drop equals 2 times K times A times D divided by circular mils, where K is the direct current resistance of copper per circular mil foot, I is the current in amps, D is the one-way distance in feet, and circular mils is the circular mil area of the conductor. For number 12 American wire gauge copper conductors, The circular mil area is 6,530 circular mils. The direct current resistance of copper per circular mil-foot is approximately 12.9 ohms at 20 degrees Celsius. Plugging these values into the formula, we get voltage drop equals 2 times 12.9 times 20 times 200 divided by 6,530, which equals approximately 15.8 volts. The percentage voltage drop is calculated as voltage drop divided by source voltage times 100%. In this example, the percentage voltage drop is 15.8 volts divided by 240 volts times 100%, which equals approximately 6.6%. Since the NEC recommends limiting the voltage drop in branch circuits to 5%, the voltage drop in the circuit is excessive. To reduce the voltage drop, you could use larger conductors or shorten the length of the circuit. By understanding the principles of conductor sizing, overcurrent protection, and voltage drop, you can design and install electrical systems that are safe, reliable, and efficient. Remember, always consult with a qualified electrician before undertaking any electrical work. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always adhere to the latest edition of the National Electrical Code and local electrical codes.